So as I mentioned in the chat, I'm happy to take a few questions. And yes, if it's about earlier lectures, that's okay. The first is from Massimo. The question is, do we use hashing and hash tables only when we know how much input we're going to get beforehand? And the answer is no. When we do know approximately how much input we're going to get, it's convenient because then we can size our hash table originally to be on the order of the number of elements we're going to insert into it. But remember, at the very end of the lecture we talked about last time, we talked about dynamic hashing, which tracked how full our hash table got. And if it ever got too full, which we used half full as our threshold of too full, we would then create a bigger hash table that was twice the size, rehash everything in the old table into the new table, and go on. And one of the things we discovered is that using amortized analysis, that still meant that the average cost of insertion was still proportional to the load factor. And since the load factor is less than 1, it's constant time, even though some inserts are very, very expensive. So the Satvik asks a question regarding deletions in open addressing. Why can't both insert and search consider a deleted item empty? They could consider deleted items empty, but insert may as well use it because a deleted item isn't really occupying any space in a meaningful way. It's only telling search that this isn't a safe place to stop looking. But insert certainly could use that space because we're not using it for anything else. That's also why hits and misses tend to cost a little. That's one of the reasons why hits and misses cost a little bit more, a little bit different. And let me see how we're doing on attendees. Getting there. We're a little shy of what we normally are on a lecture day, so I'll give it another minute or two. And again, if anyone has questions, feel free to fire them in the chat. So your asks, if we only want half of our hash table filled, does it mean we initialize the hash table to twice the size of the input if we know that size beforehand? And in that case, the answer is no. Well, it depends. If we're using open addressing, then we probably want to have this 50% threshold. So if we're using linear probing or quadratic probing or double hashing, and we're storing elements actually in the table, then having it be about half the size of the total number of inputs we're expecting is a good idea. If we're using separate chaining, however, that's less of a concern because separate chaining, given a good distribution of the hash function, doesn't have this sort of performance cliff as you get to having a full table. With separate chaining, the performance gets slower very, very gradually instead of very dramatically as it does for open addressing. So if we're using open addressing, yes, we want our hash table to be about twice the size of the input we expect. If we're using separate chaining, we want it to be about the size of the input we expect. So the follow-on question is about search. Why does search consider a deleted item full and not empty? So suppose we have our hash table and there's a cluster that's full and we want to insert something somewhere in the cluster. So we hash to this point in the cluster. Using linear probing, we keep sort of bouncing around until we find the spot for it to exist. Okay. Now imagine that we delete something. We delete something from here. And now we want to search for this item again. So if we're searching for this item again and we stop at a deleted element, we'd go here, 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 and we'd say, oh, it's not in the table, but it is in the table because we put it up higher. So that's why we want to consider a deleted item as occupied for search, but unoccupied for insert. Okay, with that, I'm going to go ahead and start today's material. Today's lecture is going to be a little bit different. This material doesn't break very cleanly into 80-minute segments, so I'm going to stop sort of in the middle of a little bit, and that's why we've combined these into one set of slides. I think I have a pretty good idea of where I'm going to stop. We'll see how things go, and then we'll move on. And Massimo, just as an aside, yes, the end condition for search, it either finds the element or it knows the element can't be there, so it's gone through the entire cluster, including any deleted spots. So we're going to start today with some fundamental definitions of how trees work and some basic ideas, and then we're going to talk about a particular kind of tree called a binary search tree or an ordered binary tree. And we've seen trees already in this class because in project 2 we implemented pairing heaps. And pairing heaps use a kind of tree structure. They're not binary trees, they're general trees, but they use a kind of tree structure. So when we looked at implementing pairing heaps in project 2, those are a form of a tree. We're going to start talking more about both today and next Thursday, more about trees in general, what their properties are and why they're interesting, and some techniques to make them very, very efficient for lots and lots of interesting purposes. So just to start, a tree is just a mathematical abstraction that captures common properties of data. So collections of data that are related to each other, plus the relationships between them given certain constraints. And trees are very, very common sorts of algorithms. We use them all the time. For example, your compiler, when it's creating, when it's evaluating expressions that are in the code, creates trees that represent the operations and operands of that expression. So this tree represents the quantity x plus 3, times the quantity y minus 2. And this is exactly the sort of representation that your compiler will use if you wrote some code int z equals x plus 3 times y minus 2, it would generate something that looks very much like this in its internal parse tree. So more formally, trees are a form of a graph. We're going to say a lot more about graphs in the coming lecture, but for now, a graph consists of a set of nodes. So we'll sometimes call those vertices. So one vertex, many vertices or vertexes. Both are okay. I usually use vertices, but sometimes I'll use vertexes. Connected together by a set of edges. So in this, A is a node or a vertex, and the line connecting A to B is an edge between A and B. So every node typically contains some data, and sometimes in some graphs the edges have data associated with them too. When we're looking at them in the context of trees, the edges only describe connectivity and nothing else. A tree is a subset, so there's the space of all graphs that are possible, and out of all of the possible graphs, so there's graphs, and trees are a subset of graphs. And a tree is a connected graph, and a connected graph is one in which all nodes are connected to all other nodes at least one way. And it's a tree if it's a connected graph without any cycles. Alternatively, it's a graph where any two nodes are connected by a unique shortest path. And these two definitions are the same. So you can describe it as a connected graph without cycles, or you could describe it as a graph where any two nodes are connected. That means they're connected. By a unique shortest path, that means there's no cycle involved in that connection. Furthermore, we often think about trees as having a designated direction where we can identify parent and child relationships. So in this tree, E is a child of B because the arrow is directed. And in a directed tree, there's one particular node that's called the root. And in a binary tree, every node has at most 2 children. So we can see that this tree is a binary tree because A has 2 children, B and C. B has 2 children, D and E. D has 2 children, H and G. E doesn't have any children. C has 2 children, I and F. And even if there was another node, K, this would still be a binary tree because I has 1 child and it's at most 2 children. So we're allowed to have 0, 1, or 2 children at any node. There are simple trees where any acyclic connected graph, an acyclic is just a graph without a cycle. Aleshua, what it means, a graph without a cycle, this graph here doesn't have any cycles, but if I added an edge to it, now there's a cycle because there's a way to, now there are 2 ways to get from this node to this node. I can go this way or I can go this way. So a simple tree is any acyclic connected graph, and simple trees don't have directions, like I mentioned before. A rooted tree is one where a particular node serves as the root. And the way to imagine this is we could pick this tree up at any point. So imagine we picked this tree up by holding that node and then we shake it. And then all the other ones sort of come out to the bottom. The node we picked it up by becomes the root. And then the weights, the way they fall, become the parent-child relationships. And in a tree, any node could be selected as the root. It doesn't matter which one we pick. Now, it will turn out to matter in terms of performance, but it doesn't matter in terms of whether or not it's actually a tree. So some more just definitions. The root is the topmost part of the tree. A parent is an immediate predecessor of a node. So A is a parent of B. A child is an immediate successor of a node. So I is a child of C because it's immediately beneath the child. An ancestor is any parent of a parent. And so let me put this in any parent of a parent. So H's ancestors are D, its parent, B, its grandparent, and A, its great-grandparent. Likewise, a descendant is any child of a child, or any child. So A's descendants are the entire rest of the tree. So all of these nodes are A's descendants. And then D, E, H, and G are B's descendants. Let me just erase this a little bit so that we have our context back. An internal node is any node that has children. So in this tree, A has children, so it's internal. B has children, it's internal. C has children, D has children. None of the others have children, so the internal nodes are A, B, C, and D. And external or leaf nodes are nodes without children. And so E, I, F, H, and G are external nodes and leaves. You will also sometimes see definitions of trees where leaves are. We can also sometimes think of these children being null, and I will often write the null pointer as the ground symbol from electrical engineering or circuit analysis. It's just an artifact of the fact that I had an EE degree when I was an undergrad. You'll see some other definitions called the null pointers the leaves. We won't do that here. We will call any node without children a leaf. One of the other really cool things about trees is that they're recursive structures. So the tree rooted at 2 is a tree, but it's also the case that the tree rooted at 6, if we just considered 6, this subtree rooted at 6, that is also a tree. If the entire structure is a binary tree, then all of its substructures are also binary trees. Because if every node at or below 2 in our tree has at most 2 children, then it must be the case that every node at or below the tree rooted at 6 also has at most 2 children, because it's just transitive. Now, the fact that trees are recursive structures will turn out to be very valuable, because many of the algorithms we write about trees, although not all, but many, will be recursive algorithms and will be able to depend on the invariance of trees being true recursively. And it will also make it easier for us to represent trees in a pretty efficient way. Some more definitions, and again, there are lots of definitions. The height of an empty tree is 0. The height of any node is 1 plus the maximum of its left child's height or its right child's height. So the height of this tree is 1. The height of this tree is 2. The height of this tree is 3. And the height of this tree is also 3. So that's height equals 1, equals 2, equals 3. The size is the total number of nodes in the tree. So the size of the tree is 1 plus the size of the left subtree plus the size of the right subtree. Again, it's a recursive definition. So in our example, the size of this tree is 1, the size plus the size of this tree, which is 2. The size of this tree is 1. So it's 1 plus 2 plus 1. The size of the total tree is 4. Depth is very much like height, except it's measured from the bottom up. So the depth of the empty node is 0, and the depth of the empty tree is 0, and the depth of a node is the depth of its parent plus 1. So the depth of the parent is 1, the depth of its children are 2, the depth of its children's children are 3, and the depth of these children is 4, because it's the depth of the parent plus 1, and we start it with 1 at the root. Okay, I think that's the definitions. There might be one more. Let's see. Nope, we're good. So let's take a minute. Just take maybe a couple minutes on your own and write down what are the roots, what are the internal nodes, what are the leaf nodes, what's the maximum depth of this tree. Pick any subtree and label it, and then answer the question, is this a binary tree? And I'll give you, it's about 12:19 for now. I'm going to give you a few minutes to think about it. I'd ask you, so Manish, hold on to questions for a minute, because I want to give people a chance to work through this themselves, and then we'll come back and we'll answer all of them together. Okay, so let's take a look at the answers to the quiz. The root is A, because it's the one at the top. Internal nodes are any nodes with children. A has children, B, C, and F. Those are the nodes that have children. The leaf nodes are all of the others, so E, I, J, K, G, H, and D. The maximum depth is 4, because this is depth 1, depth 2, depth 3, depth 4. This is a subtree. You could pick anything. D is a subtree, K is a subtree, B, any node becomes a subtree. And is it a binary tree? And the answer to that is no, for 2 reasons. One, A has 3 children, and F also has 3 children. So it's not a binary tree. And Monish, to answer your question, the height of A is also 4, because the height of the tree is always the height of the tree at the root is always equal to the maximum depth of the lowest leaf. Okay, so that's the set of definitions. Now we're going to move on and talk about a subclass of trees called binary trees. And as I've alluded to already, a binary tree is just a tree that where every node has at most 2 children. And we're going to add an extra sort of condition to our binary trees that we're going to care about. We also might want to have some ordering between the nodes, and we'll talk about that a little bit today as well. So a binary tree is an ordered tree. There is a linear ordering for the children of each node. So there is a less than relationship, just like there was a less than relationship when we talked about heaps, and just as there was a less than relationship when we talked about sorted order, and there's also an equality relationship. And remember, from less than and from equality, we can define all of the other comparators. So there's going to be an enforced ordering for the children of each node, and a binary tree is an ordered tree in which every node has at most 2 children. And there are a couple different ways to implement this, and we'll look at those. The first is with an array. So remember, when we implemented heaps, heaps are represented as a form of a tree. In heaps, we talked about something that was really convenient called a complete binary tree, where the tree has some depth, and the depths, so here's depth 1, here's depth D. At depth D minus 1, the tree is complete. In other words, there's a node everywhere in this parent tree, and that all of the elements at the level of D are in their leftmost position. So this is a complete binary tree. So if you were going to add a node to a complete binary tree, it would have to go right there, because that's the only place it could go. So that's a complete binary tree. And remember, we talked about complete binary trees when we implemented heaps. And heaps, the heap invariant, which said this node has to be more important than every node below it and recursively true, that allowed us to implement a heap in an array as a complete binary tree. And if you remember from when we implemented heaps in project 2, the binary tree array implementation was pretty simple. Well, it wasn't simple. I actually had to debug. I had several bugs in mind. So it was easy to explain. It was a little less easy for me to implement. Let's put it that way. The root was at index 1. The left child of any node at index I is 2 times I. The right child of any node at index I was 2 times I plus 1. Now the difference between a complete tree and in general a binary tree is that some of these indices might be skipped. Because in a binary tree we have a more constrained ordering among the elements than we do in a heap. So in a heap, the only constraint was the node rooted any tree or subtree was more important than all of its descendants. For an ordered binary tree, we can think of a node and its 2 subtrees. The left subtree contains all the nodes that are less than the parent, and the right subtree contains all the nodes that are greater than or equal to the parent. Now it turns out when we have this constraint, so this is the binary tree constraint, this was the heap constraint. When we have the binary tree constraint and we insert a new node into an existing tree, there is only one place it can ever go, and it's not necessarily the place that would form a complete tree. And so in a binary tree, we may end up skipping some indices. And so if we're going to implement a binary tree in an array, it can be very expensive in space if our tree is, quote, sparse. And so a sparse tree is one where instead of having a complete tree, maybe we have some nodes here, some nodes here, some nodes here, some nodes here. And this is a binary tree, but it's very, very sparse because it's not complete. There are lots of holes in this tree versus what we would see in a complete tree. But for completeness, we'll talk about what the expense is. The best case that we inserted a key, we happen to pick the right place to start with. But the worst case, we have to check every possible location of all of the leaves. There are approximately n over 2 leaves, so that's approximately linear. The same is true for remove, and remove it could be very expensive if we have a tree that's kind of a stick. So we have to check each element until we find the right one to remove. So that's linear. However, parent in a binary tree implementation, in an array-based binary tree implementation is really cheap. It's the index over 2 and the floor. The child is also really cheap. It's index times 2 or index times 2 plus 1. In the best case, if it happens to be a complete tree, it's very efficient in space. It's linear. You have to represent all of the elements. You can't do better than linear to represent n elements. You need n pieces to do it, assuming they're unique. We'll come back to that in a minute when we talk about compression later in the class. But in the worst case, it's 2 to the n. And it's 2 to the n, again, when we have a stick. So trees can be very bushy, so really complete, or they can be very sparse and sticky, or like a stick. And when trees are like a stick, then they're pretty bad for us. And Elliot, yes, best case for remove is also linear, because to remove something first, you have to find it. So we don't typically use arrays to represent binary trees because many binary trees are sparse. And so, and Satvik, the complete, this is for a binary sorted and ordered binary tree. Ordered binary trees are by definition potentially sparse. For a complete tree, in other words, if it were a heap, all of those operations would be logarithmic, because remember, in search, we don't really remove arbitrary keys. We only remove the top if it was a heap. And for insert, there's only one place we put it in and then we fix up. That was logarithmic. So if it were a heap ordered tree, we can guarantee that we can represent it as a complete binary tree. For an ordered binary tree, which is not the same, remember, an ordered binary tree is this version where everything in the left subtree is less than the root, everything in the right subtree is greater than or equal to the root. What's the difference between using the initializer list with curly brackets and parentheses? That's a question I actually don't know the answer to. I am about 2 standards behind in my deep knowledge of C++, so that's one I would have to look up. So the yeah, and again, I wish I knew the answer to that. I know that you can use both, and I will come back when we talk next time on Thursday with an answer to that. Drop me an email, Agam, and remind me that I'm going to do that for us. So instead of using an array, we almost never use arrays to represent binary trees. Instead, we use pointer-based structures. And again, we've already seen this because in project 2, we built a pairing heap. And a pairing heap happens to be implemented with pointers instead of as an array. So typically, it's a templated class. The class contains some data. It's stored in the thing called key. It has a left subtree, which is by default the null pointer, a right subtree, which is also by default the null pointer, and we initialize the value key to whatever the user has passed to us. Elliot, yeah, it might just kind of look cool. I don't actually remember the details, and again, I'll go back and look them up. As for whether people choose the, and again, we'll have to, after I can tell you what the difference is, then I can tell you why we might choose one over the other, but I don't have a good answer for that right now. So a node contains some information, the key, and it points to its left child and right child. So sometimes I will draw that as K, left, right. And it's very efficient to move down the tree. It's not very efficient to move up the tree because we have no easy way of getting to it without walking the entire tree and finding it. So now inserting the key, best case, is constant time. So inserting into an empty tree, pretty easy. That's just going to go at the root. Inserting a key in the worst case, still linear, and it's linear if we have a tree that's a stick. Remove key, again, we have to find it to remove it, still linear. Finding the parent is now linear because if we have some node that's deep in the tree and we want to find its parent, we have to start at the top and walk the entire tree until we find the one that happens to point to it. So that's linear. Turns out we're not going to need to do that very often, and I'll come back to why that is in a second. But the intuition for why is that because trees are recursive structures, we either can pass the parent pointer along as we descend in the recursion, or as the recursion unwinds, we're back to a place where we know where the parent was because the recursive call returns to that point. So recursion gives us sort of an easy out for not being able to remember the parent. Child is constant. The space in the best case is linear because we're going to represent every element with 3 items, and O of 3 is per element is O of 1 per element. There are n elements. That gives us linear space in the best case and in the worst case because the representations are exactly the same. So we get a much better, anytime you can take something that's exponentials are horrible and bad. Whenever you see an exponential, you have to go running, screaming from the room and avoid them at all costs. So anytime we can convert an exponential to a linear thing, that's a huge win. So binary trees using pointers, and this is a pointer-based binary tree. Binary trees using pointers, big win. Okay, there is another way to do this. If for some applications, if we need a cheap way to get to the parent, we add the parent pointer explicitly. If we have a parent pointer in our implementation and the node is the root, then the parent is null. Otherwise, it points up to its parent. This is very uncommon. Again, it's not common because for most applications of trees, we don't really need to get to the parent cheaply because most of the time we have a recursive function that gives us an easy out for being able to do that. Now it turns out, as an oddity, this is kind of just a sidelight, but it is interesting to think about. It is always possible, given any general tree, to by construction create a binary tree. So this is a mechanical transformation, and it's sort of like the transformation, if you remember from 280, when we converted tail recursive functions into iterative functions, and there was just an algorithm for being able to do that. Same thing, there's just an algorithm that takes a general tree and creates a binary tree out of it. The intuition behind how this works is that if we have a node with some number of children, C1, C2, C3, C4, we convert that into a binary tree by having C1 be the left child of the new node, and its siblings become the right children of this. So C1, C2, C3, C4. So that's not a very efficient structure. Notice now we've converted this very bushy tree into a stick. but it does work. And then we can just recursively descend through each of these structures and do the same thing. And so the idea is that when we're moving left, that's a new generation, and right are siblings. The root doesn't have any siblings, so the root's right subchild is always null. But the rest of the tree might be bushy, or it might be sticky, or more stick-like. Shouldn't use sticky, more stick-like. So imagine we wanted to do this with A, and what I'm going to do, there's a little animation, and the animation might run a little quickly, so I won't talk about it so much, but I'll come back and point out how it worked. So we'll start with the node A. Its leftmost child is B. C and D are its siblings. B's leftmost child is E. F is its sibling. C's leftmost child is G. H is its sibling. F's leftmost child is I. J and K are its siblings. And so this is a mechanical construction, and I actually managed that. I couldn't do it in practice, and it might have gone a little fast. So I'm going to talk about it again, just in case that was faster than anyone followed. So B is the leftmost child of A. C and D are its siblings. B's child, and now we're going to recurse, so we're going to call it for B, C, and D. B's leftmost child is E. E's sibling is F. C's leftmost child is G. G's sibling is H. And for D, there's nothing to do because D is a leaf, so we're done with D. Now we recurse E, leaf, we're done, nothing to do there. Recurse F, F's leftmost child is I. J and K are its siblings. G is a leaf, H is a leaf. I, J, K are leaves, we're done. So it's a simple recursive algorithm that, given any tree, can generate a tree that's guaranteed to be a binary tree. Okay, we're going to take a pause. We've been going for a little more than just about 40 minutes. I'm going to just take maybe like a 3-minute pause, collect yourselves if you want to check email. We're going to reconvene at 12. It's 12:38 right now. We're going to reconvene at 12:41. Okay, let's go ahead and pick things back up where we left off. The next thing we're going to do is we're going to take a look at some algorithms that work on sorted binary trees. And the first family of algorithms we're going to talk about are traversals. So in other words, given a tree, how do we process the nodes in the tree? If we want to compute over the tree and either print them all out or maybe add one to every node or do something else, if we wanted to iterate over every node in the tree, how do we do it? And it turns out there are a couple different ways to make this happen. And we're going to talk about 4 of them. And the first 3 are recursive descents. And the last one is an iterative descent. So the first one is pre-order, and for the recursive ones, so all of the recursive ones have the same form that in the function they're going to call function on left, function on right. And the question is whether we deal with the node before we recurse in any of them, between the 2 recursive calls, or if we do it afterwards. So in pre-order, we visit the node before we recursively visit the 2 subtrees. In order, we visit the node between recursively visiting the subtrees. So it's in between. So pre is before, in is in between. For post order, we're going to recursively visit the trees and then visit the node last. And something called level order, which is also called breadth. Sorry. It's one of those times when I need to be a little more careful about how I'm writing. Level order is sometimes also called breadth first, because we're going to examine the breadth of the tree. The others are all depth first. So the 3 recursive are depth, first. The level order is breadth first, where we go each level, we go broad instead of deep. Here are the implementations for each of those, and the implementations. One of the cool things, I love recursion. I'm a big fan of recursion. I'm hugely into recursion. Recursion is great, and the reason I like recursion is once you've written down the recursive definition of something, the code for that is just translate the definition directly into code, and it makes a lot of sense. The recursive version of the pre-order, if we have the definition of the node we had before, where we have a key and a left and a right, is we visit the key, process the key, and then we recurse. The definition of post order is we recursively descend through the trees and then we visit the key. And the difference, the version of in order is we recurse on the left, then we visit, then we recurse on the right. And yes, I definitely sense this. Let me actually take a break. Let's take a minute because I'm seeing a lot of chat in the chat about the projects. I think it's probably worth talking about it for a second. There are lots of different ways to attack a project in 281, and I will tell you my favorite way. My favorite way is I print the spec. I go to a quiet place. Now I used to go to my favorite cafe or the library on the west side, which has a cafe attached to it. I don't get to do that anymore. So I go to the couch in the back here. I print it out, I get under a blanket, and I read the spec from beginning to end. Then I put the spec away, and I don't look at it again for at least 24 hours. And I go work on something else. And then the next day I do the same thing. I get under the blanket, I pick up the spec, and I read it, and I start circling the things that I don't remember ever reading before. And there are usually a lot of things that I'm circling that I don't remember ever reading before. But after I've read it a couple times, then I start thinking about sort of the big picture architecture of how I want things to work. And I talked about this a little bit in one of the video explainers that I posted earlier in the semester. I think about structuring my program a lot like I think about structuring an essay, where the functions are like paragraphs and each function should do one thing. So I start plotting data structures, start plotting functions, and then I'll fill out little bits. One of the things that I really encourage you to do next is, once I build some little piece of the program, I test that little piece right away. So for example, when I solved project 2 and I wrote the comparator for the heap, for the Jedi comparator and the Sith comparator, the very first thing I did was hand code a bunch of deployments that had some ties, and I dropped that list of deployments into the Jedi heap and into the Sith heap, and then I pulled them out again to see if they were right and printed them. And sure enough, I had gotten the tiebreakers wrong. Now I found out that I got the tiebreakers wrong right after I wrote the function, instead of days and days later when I got the feedback from the autograder that said, if your error is on line 472, you might be breaking ties wrong. So incremental building and incremental testing is really, really helpful. But I do one more thing, and this is my most important. So if you remember none of the rest of my advice for the rest of your careers at Michigan and beyond, remember this piece. Because the next thing I do is that every time I'm working on something other than the project and I need a break, I keep a copy of the printed spec next to me. And I put a sticky note where I stopped reading it. And whenever I need a break, just a couple minutes, I'll pick up the spec and I'll read the next 2 or 3 paragraphs. And then I'll put a sticky note down. And when I read those next 2 or 3 paragraphs, I'll take a note of things I never remember reading before. And I keep doing this until one of 3 things happens. 1, the deadline arrives. No sense working on it after the deadline. 2, I complete the project and pass all the test cases and I'm happy with it. Or 3, I have read all the way through the spec from beginning to end and haven't found anything that I thought was surprising. Now, if I'm not the one who wrote the project in the first place, which is true for all of the 281 projects, true for some of the 482 projects, and it's even now true for a couple of the 280 projects. If I wasn't the one who wrote the project in the first place, 3 never happens. I never get to the end of one of these full reads of the spec without realizing, oh, I don't think I ever remember seeing that, or oh, I don't think I did that, or something that jumps out at me as a surprise. That's because these things are complicated. They are complicated to the point where it's really hard to keep everything in your head all at once and expect to have all of the details right. Now, some of that could be because I'm 52 and my brain has deteriorated to the point where I just can't do it anymore. But I don't think so, because this has been true for me for a very, very long time. So continuously reading small chunks of the spec, and you only want to read 2 or 3 paragraphs at a time, because if you start reading a whole bunch more than 2 or 3 paragraphs, you're going to start glossing over stuff and you're going to miss the things you missed the last time you read it. Or at least I do. Let me use this in I phrasing. I will miss things. If I read more than 3 paragraphs at a time, I will start glossing over details and I'll miss the same details that I missed the last 4 times I read this. So slow incremental reading is really, really, really helpful. Okay, pop the stack. Let's come back to the recursive implementation. So as I mentioned, the recursive implementations, and Matt, that's a really good, skim it and then read in more detail. A recursive read of the spec is also a really good way to do that, and I think I find myself doing that with longer specs as well. That's really good advice. So again, the recursive versions, they all recursively call left and right, and the question is just whether I visit before, in the middle, or after. In pre, I visit before. In, I visit in the middle. In post, I visit after. And post visit is just whatever we're doing with the element. And for now, let's think of visit as being print. So we'll think of it the same way. All right, so to summarize, pre-order, in order, and post order are all depth first recursive. traversals, level order is breadth first, and it turns out we will write this iteratively when we get to that point. Okay, so take a moment, and given this tree, and remember, it's the form of our functions is recurse left, recurse right, and we either visit pre, in, or post. So pre, in, or post. So given that general form of recursive descent and this tree, what order do the nodes get visited if we're visiting in pre-order, in order, post order, or so these are the three recursive versions, or level. And remember, level is breadth first, where we do all of one level before we come to the next one. So for take just a couple minutes, maybe 2 or 3, and take a look at the nodes, take a look at this and see if you can come up with the pre-order, the in-order, the post-order, and the level order of each of these. I need to get the Jeopardy theme music that we can play while we're doing this. Okay, let's take a look. So for pre-order, we're going to visit, then left recursive, visit, then left recursive, visit, then left recursive. That's that, we're done. Right recursive, we're done. Pop. Right recursive, we're done. Pop. Right recursive, visit. Left recursive, visit. So 0, 1, 2, 3, 4. Ah, excellent. So 0, 1, 2, 3, 4 was good. In order, we recurse left, recurse left, recurse left, recurse left, we're done. Pop, 2, recurse right, pop, pop, visit 1, recurse right, pop, visit 0, recurse right, recurse left, left, pop, visit right, pop, visit right. So this is 21043. 21043. And then for post order, we recurse left, 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 pop right, visit, pop right, visit, pop right, left, left, pop right, visit, pop right, visit, pop visit. So I think that was 21430. 21430. Excellent. And then level order. Level order is in some sense the easiest one, because for level order, we're just going to start at the root and then 1, 2, 3, 1, 3, and then 2, 4. So it's 0, 1, 3, 2, 4. 0, 1, 3, 2, 4. Now, that's given a tree, you can compute its various traversals. One of the other cool things is that given 2 traversals, you can order the tree. You can draw the tree. Now you can't do it with just one, because, for example, if we only had pre-order, well, we know 7 is the root, because it prints before it descends. So 7 is definitely the root. But 3, for pre-order, we don't know where it could go. It could go either left or right. So we're going to use some other traversal to tell us how to do that. And this example will walk through both of those. So for this, we know that 7 has got to be the root. That takes care of 7. 3 is the next one that we're going to consider. 3 could be either 7's left child or the right child. We don't know yet. Now, because 3 appears to the left of 7 in the in-order traversal, that means 3 must be on the right-hand side. And sure enough, on the left-hand side. So I will also apologize. I periodically confuse left and right, but I do it non-deterministically. So I will, with some probability p that is greater than 0 and less than 1, and actually close to about maybe 0.3, I will say left when my brain is thinking right, or I will say right when my brain is thinking left. Now, back in the days before GPS, which I know probably none of you remember, but there was a time when we didn't have GPS routing and we had to use paper maps to get hither and yon. And if I was the navigator and my wife was the driver, I would occasionally say, go right, pointing left. And she would respond, do you mean left, right, or right, right? And I said, oh, of course, left. Of course I meant left. As a result, I was very rarely allowed to be the navigator, and I was usually the driver, because if she said left, I would do the right thing, but I couldn't produce the right word. So I will probably do that, and I will apologize. Okay, so we've placed 3. Now we want to place 6. 6 can be the children of any of these. So it could be the left child of, or the right child of 7, or it could be either child of 3. Well, 6 is to the right of 3, but the left of 7, so it's to the right of 3, but the left of 7, so 6 has to go right here. And once we've placed 6, we know nothing can ever be to the right of 3, or to the left, sorry, to the left of, I have to do this permanently, to the left of 3. And so we no longer need to consider that as our next segment at all. So that's place 6. Now we have to figure out what to do with 9. Well, again, 9, if we're only using pre-order, can be in any one of these 3 positions, but if we look at 9, it's to the right of 7, so it has to go to the right of 7, and that's where it lives. Takes care of 9. Now we're looking at 8. 8 could go in either child space of 9, but because it's to the left of 9, it has to go there. 13 could be either child of 8 or the right child of 9, but 13 is to the right of 9 in the in order, so it has to go here. And once it goes there, that means nothing else will ever be to the left of 8, because we haven't gone there anymore. And then finally, we can do the same thing with 27, and 27 lives to the right of 13. Elisha, I can't imagine getting anywhere without a GPS anymore either. In fact, it is amazing how fast I lost some fairly important spatial reasoning abilities once I started relying on a GPS. I just stopped thinking about where things were because it tells me and I don't have to think about them anymore, which is pretty interesting. Okay, if we're going to do a level order traversal, that's breadth first. And so the next thing we're going to do is look at a function that does that. And I'm going to build this function one line at a time. So the first thing we're going to do, remember that we're going to start, the argument to this function is the root. I think I have the wrong. No, I have the right one. Weird. Oh, interesting. It does sensors. I forgot about that. I was pushing too hard on it. Cool. So we're passing in the root. The tree could be empty. So the first thing we have to do is check to see if it's an empty tree. If it's an empty tree, we just return. There's nothing for us to do. If it's a not empty tree, what we're going to do is we're going to use, this is going to remind you a little bit of the Q search from Project 1 when we were searching for the princess. So in Project 1, when we were looking for, it wasn't Princess Peach, I forgot what we called her, in the hopes that we weren't violating copyright somewhere. When we were looking for the princess, we would insert things in a queue and then we would pull them out. Countess Cherry, thank you. So what we're going to do, we're going to work similarly to the way we did when we started at the start location in that search. We primed our queue with the start location and then we had an iterative algorithm that worked on it. We're going to do the same thing here. So we're going to have a queue of pointers to nodes. And we're going to push the root into that queue to seed the queue. And then we have a while loop that's going to iterate, and as long as the queue is not as long as the queue is not out of nodes, we'll continue to be able to revise them or continue to be able to search through them. So as long as the queue is not empty, we're going to get the front, and then we're going to pop it. Yeah, imagine getting a cease and desist from Nintendo. It could happen. Yeah, no doubt. And this is another idiom where we see this idiom a lot, where we take a front and we pop immediately afterwards, so that we know that we've, quote, removed it from the queue. We'll print it. If this node has a left child, we'll push it into the queue. If the node has a right child, we'll push that into the queue. And then we'll return. And so the idea is, at the root, we'll first push all of the children, the left child and the right child, into the queue before any subtrees are examined. So we're going to get both of these before we get any of these. And because we're doing this in queue order, we'll do the same thing. So when we pull the left child out, we'll get the left child's children first. Then we'll pull the right child out and get the right child's children first. And then because it's a queue, we're going to go here next. So we get this behavior of sort of a winding descent down the tree. Okay, so that's the basic idea. So yes, it is similar to some of the functions in Project 2. So for example, when we removed the top element of the pairing queue, and then we created a queue that did pair creations. I actually did mine in something that looked more like a stack, because I did the forward and then backward version. But there are lots of ways to do it in a queue, an iterative queue, until it's just got one thing left, is another way to have done Project 2. So the question is, why do we node queue front and then pop right away, instead of using queue front and pop at the end? So I like to use, there are two parts to this question. The first is, why do we create a variable for queue front instead of just reusing queue front? I like that for a couple reasons. One, if you keep reusing queue front, that continues to call that function over and over and over again. Now, it may be the case that the compiler can optimize that away in some circumstances if it knows that there are some, but it's very rare. So I want to call this function exactly once and store the result in some local variable, so I don't have to keep calling the function over and over again. The second piece of that question is, why do I pop right away? And the answer for me is, I want to pop as soon as I know it can be popped, because otherwise, if it's a long function, it's easy to forget. So this idiom says, remove the top node and use it. If I push the pop down later, it separates the removal from the use of it, and that makes the code for me, it makes the code a little bit harder to read. And yes, front is order 1, but function call and function return cost you something. And maybe when we come back next time, so I have 2 things that I have to do. I have to look up curly braces, and we have to look at the costs of function call and return. Because function call and return can cost you something, because you have to push things onto the stack and pop things back off the stack, and you have to keep doing that over and over. And if you can avoid doing that work, it's better to avoid doing that work. It's much more pleasant to avoid it than to do it if you can get away with it. Okay. The best code is no code. Yeah, I'm a big fan of writing as little as possible, because every line of code I write with some probability P has a bug. And my value of P is pretty high, it turns out. Other people's values of P might be lower, but my value of P is pretty high. Okay, so getting back to this binary search, this ordered business. Remember, I talked earlier in the lecture about the idea that the root has a left subtree and a right subtree. In the left subtree, all of the nodes are less than the root, and in the right subtree, all of the nodes are greater than or equal to the root. So that's this same thing in text. The key of the node is greater than things in the left subtree and less than or equal to the things in the right subtree. Now, one of the other cool things about this is that means insert is almost exactly the same as search, because it turns out that with this constraint, when we're adding a new element, there is exactly one place it can go. And it's defined by this recursive invariant of the binary search tree property. So while we're inserting, we just search until we find where that node would have gone. And once we run into a leaf, we put it where that leaf points. And then we're done. Okay, very, very cool. So this is 2 different versions of the same set of data. So notice everything in the first tree, everything to the left of 6 is less than 6. Everything to the right of 6 is greater than 6. At the subtree rooted at 5, everything to the left of 5 is 2. Everything to the right of 5, everything to the left of 5 is 2. Everything to the left of 5 is less than 5. Everything to the right of 5 is greater than or equal to 5. They happen to be equal, but that's okay. And same thing with 7. There's nothing to the left, and everything to the right of 7 is greater than or equal to 7. This is the same tree, or the same data, in a different shape. But it still works, because everything to the right of 2 is greater than or equal to 2. Everything to the right of 5 is greater than or equal to 5. Everything to the left of 7 is less than 7. Everything to the right of 7 is greater than or equal to 7. Everything to the left of 6 is less than 6. So one of the things that's interesting, the take home about this particular example, is that the shape of the tree depends on the order in which elements are inserted. So order of insertion dictates shape. And we'll see why as we develop this going forward. But that's the essential idea. And remember, the other thing that we've been thinking about when we talk about trees is that bushy trees, or the more complete the tree is, the more efficient it is, because the depth is log. And the more like a stick a tree is, the worse it is, because the depth becomes linear. So the order in which we see elements inserted into our binary search tree will determine whether our tree looks more like this really dense shrub-like thing, or more like this really awful stick. And yes, Joseph, the idea is the root can be anything, and the root will be the first element inserted into the tree. Because when we start with an empty tree and we insert a root, the new node becomes the root, and that's where it goes. And then if we insert the next element, we're going to check to the left or right, depending on whether the next element is less than or greater than or equal to. Okay. So to sort of bring this home, let's think about this tree, and we'll write the output for in-order, pre-order, and post-order traversals of the binary search tree. In order, so we recurse, left, 2, pop 5. Oh, and I'm gonna underline the second 5 so we know which order it was visited in. 5, pop, visit 6, no recursion, pop, visit, no recursion, pop 8. So the in order is 2, 5, 5 underscore 6, 7, 8. And as we looked before, I'm not going to go through the details of pre-order because it's a little less interesting, and the same with post-order. But remember, pre-order, the root is always the first one. Post-order, the root is always the last one. One of the other things about pre-order and post-order changes the order in which these two 5s appear. Pre-order and in-order happen to preserve them. Okay. But one of the things that with this definition, there's something kind of interesting about the in-order traversal. And the in-order traversal is in order. That will turn out to be kind of interesting. Which I kind of gave, I forgot that this was going to be a question I was going to ask you. So given that the in-order traversal is in order, that gives us a way of sorting something using a binary search tree. Because if we just insert all of the elements into the tree and then do an in-order traversal, they're going to be in order. Because again, if we have a node and a left subtree and a right subtree, and these are all less than, and these are all greater than or equal to, we're gonna, if we're using an in-order traversal, we're gonna print all of the less than things before the node, and then all the greater than or equal to things. And since that's a recursively true property, that will work all the way down to the leaves, and this will end up sorting our tree for us. So a binary search tree, where we preserve the binary properties of less than or greater than or equal to, this turns out to be an incredibly powerful and cool data structure. Okay, so I think I have time to do one more topic before we'll close for the day, and then we'll pick it up here when we come back a week from today, because next Tuesday is a wellness day, so I won't be giving a lecture next Tuesday. So how do we think about search? How do we find a key in the binary search tree? And so the idea is that we're going to return a pointer to the node that contains this key, given a root and the key we're looking for. And this is going to return the pointer to the node containing the key k if it exists in the tree. Otherwise, we're going to return the null pointer. And remember that the key, because of this binary search tree property, the key of any node is greater than the key of all of the nodes in its left subtree, and it's less than or equal to the keys of all the nodes in its right subtree. So we'll think about what are the average and worst case. We'll think about how to do this, and then we'll think a little bit about what the average complexity of this is and what the worst case complexity of this is. So first, let's think about search. So the way search works, and I'll just let me give the intuition on this page. We're going to start at the root. If the root's empty, it's not there, we can return null pointer. But if the root exists and it's the thing we're looking for, well, then we're going to return that node. If the root isn't what we're looking for and it's greater than what we want, we're going to look in the left subtree, because if it exists, it would have to be in the left subtree. If it's not the root, but it's less than, but the root is less than the thing we're looking for, it has to be in the right subtree, because everything in the right subtree is greater than or equal to. So if the root is greater than the thing we're looking for, we're going to search in the left subtree. If the root is less than the thing we're searching for, we're going to search in the right subtree. Okay, that's the intuition behind the algorithm. and this is the algorithm implemented. So it's gonna be a recursive. We're actually gonna write this iteratively. You could write it recursively, and what I might do is write this recursively and bring it to start with us next time. But we're gonna do it iteratively for now. So the first thing is we could have been past the null, the empty tree, and if it is, we better not actually dereference it. If it's not the empty tree, then we can compare the root of this tree, or the node we're currently considering, with the key we're looking for. And I want to make an aside on this. In the exam in question 26, I graded a number of question 26s, and many people used the following structure. They would say if something like Q top and not Q empty. And that turns out to be unsafe, because when we have a logical AND, we evaluate it from left to right, short circuiting. So if the first condition is true, or sorry, if the first condition is false, we know the whole thing has to be false. We don't have to evaluate the second condition. But if the first condition is true, then we have to evaluate the second condition. In this case, we don't evaluate the second condition until after we've evaluated the first condition. And this is unsafe. If it's empty, it's undefined. So just sort of as a side note that I wanted to mention, something that I saw pretty commonly. I would say I saw that 1 out of every 5 or 6 exams that I graded in question 26. So that was a fairly common error, and it's one that can get you into some pretty serious trouble down the road. Okay, so coming back to our example, if we haven't run out of room, I've had a lot of seg faults doing this too, which is how I've learned it the hard way. If we haven't run out of the tree, so if we haven't gotten to the bottom of the tree and found nothing, and the thing that we have is not the thing we're looking for. Well, if the key is greater than what we're looking for, or what we're looking for is less than the key, it has to be, because remember, there's the key, here's the left subtree, which is less than, here's the right subtree, which is greater than or equal to. If what we're looking for is less than the key we're currently considering, then we're going to check the left subtree. Otherwise, well, it's not equal and it's not less than, that means it has to be greater than, we're going to check the right subtree, and then we recurse. So if we were looking and it was in the left subtree, then then x starts here, x moves from there to point to this left subtree, and we'll just descend, we'll make our way down the tree. So if we have some tree, we start at the top and we sort of make our way down the tree until we either find the node or we run out of room. So if we find the node, then x points to the node that contains the key. If we ran out of room, then x is the null pointer. Either way, returning x is fine. Sorry, I kind of made that a little unreadable. Let me erase that. Okay, so search will run on the order of the height of the tree. Okay, now if the tree is really wide and bushy, the height of the tree is logarithmic. If the tree is a stick, the height of the tree is linear. So the runtime of search depends very, very much on the overall structure of the tree. And when we come back, we'll come back and we'll look at an example. In fact, well, let me do the example really quickly, just because I know we're at time, but let me use 1 more minute. So if we're looking for the key 9 and we're going to start at root, well, 9 is less than 15, so it has to be in the left subtree. Then we're going to consider 6. 9 is greater than 6, so it has to be in the right subtree. Then we'll consider 7. 9 is greater than 7, so it has to be in the right subtree. Then we'll consider 13. 9 is less than 13, so it has to be in the left subtree, and we found it. Okay. And if we were searching for something that didn't exist in the tree, say 23, well, 23 is greater than 15, it has to be in the right. 23 is greater than 18, it has to be in the right. 23 is greater than 20, it has to be in the right. Whoops, there's nothing there. We return the null pointer. Okay. When we come back, we'll see how we can start working on some of this. So, yes, Agam, the question is, if we had the line of code, if false and undefined, that's safe. This is called a guard. Yeah, and so sorry, you typed in the chat before you saw my response, but yes. So when we have this structure, so we'll say if not x and x k equals 3. This is called a guard. So if not x is false, then it doesn't evaluate the rest of this, and it's totally okay if, or sorry, this would be if x. Okay, so if x and x dereference k equals 3. So this will only evaluate the second half if this is not null. So this guard is one of the, this is a pretty common technique. We use it quite a lot, and it's a way of being able to track, oh weird, I wonder why it's doing that. It's a way of being able to track what's going on. So with that, I'm going to pause today. We'll pick up where we left off next time. And Monish, you have a question about one of the lectures on strings. Please feel free to fire it away. And I'll stick around for a few more minutes until 1:30 if people have other questions they want to put in chat. Otherwise, I will see you in a week, and enjoy decompressing a little bit on Tuesday. And good luck continuing with Project 3. So Monish, go ahead and fire away. Is it true that the string A is less than the string B is less than the string C? And I believe the answer to that is yes, because the less than operator is defined for standard string. In fact, let me pull that up real quick. So the less so string does defined. So the question is, if that's true, how come when I do quotes A and quotes B in C++, you get false? That's because quote A in C++ is a C-style string, not a C++ string. Okay, and so what you're really comparing with C-style strings, comparisons are on the pointer to the first character, not the string itself. So if A happens to appear before B in memory, that will be true. If A happens to appear after B in memory, that will be false. So this is one of those times when managing the difference between C strings and C++ strings is really, really important. So if you said string A equals A, string B equals B, then A less than B would evaluate to true. Okay, if you think that doesn't work, I will double check it and make sure that it does work, and I will report back. So I have 3 things to report back on: curly braces, a recursive version of binary search, and string comparisons, and whether they are defined lexicographically or not. Okay. And I'm happy to take other questions if anyone has more.